Hello. If you're curious, yes, I'm eating uncooked ramen noodles. Hello. Hope everyone's doing well. Waiting for 15 people. Okay. I'm gonna go ahead and get started. Um, so I realized back when we were discussing energy, um, I forgot to talk about power. Okay? So we're going to talk about power today. And, okay. And this is going to correspond to Energy Quiz 4. All right. Um, so let's discuss it. So power is denoted by P, unfortunately the same variable as momentum. And but usually it's a capital P, and usually momentum is a lowercase p. And power is the rate at which work is done, the derivative of the work with respect to time. Okay? So that means that the units of power are units of work divided by units of time, which are joules per second, which is also known as the watt, W. So power is measured in watts. By the way, this is going to be a really short lesson today. All right. So work, you might recall, we have two formulas for work. We have the formula integral of force dx, and we have the rotational work, which was the integral of torque d theta. Okay. So I'm going to take the derivative of these with respect to time. Now I'm going to do a little tricky trick. Check this out. I'm going to divide by dt, and then I'm going to multiply by dt. So that's the same. I can do that because I'm just multiplying by 1, right? Because it's dt over dt. I can just cancel out the dt's and I get back to where I started. I'm going to divide by dt, and I'm going to multiply by dt. Okay? So you might notice that we have dx dt. That's just the velocity. So we have that work is the integral of force times velocity with respect to time. Okay? And then here, the derivative of angle with respect to time is just angular velocity, which is omega. Okay? So now I can take the derivative with respect to time. I just use the fundamental theorem of calculus, all right? So if you have the integral of g of t dt, if that's I, some integral, then di dt just gets rid of the integral sign in the dt, and it just equals g of t. So when I take the derivative, d work, d time, that's just going to equal force times velocity. And when I take the all right. And when I take the derivative of that with respect to time, I get torque times omega. So that means the rotational power is torque times omega. All right? The sort of like linear power is force times velocity. This equation is actually, this is the one-dimensional equation for work. But if you have fully three-dimensional, this becomes the dot product of the force vector with the velocity vector. Okay? So these are our two equations for today. All right. So what I'm going to do is I'm just going to play around with these equations a little bit, and then I'm going to be done. Okay. So let's suppose you have an airplane. Okay. And an airplane has 4 forces acting on it. It has the thrust force, F sub T for thrust. It has the drag force. And the drag force, we used in class, we used the equation CV for drag force, but actually for airplanes, it's more appropriately modeled by CV squared. It has the lift force, and it has the weight force. So now if a plane is in level flight, the lift force has to match gravity. If the plane is in level flight at a constant speed, then the thrust force has to be matched by the drag force. So these two also have to be equal to each other. Okay? So what that means is that the thrust force has to be equal to CV squared. Okay? So what does that mean about the power output of the engine? Is the thrust force times the velocity of the airplane. Okay? And so the thrust force has got to be equal to CV squared, so I have C times V squared times V. So it's CV cubed. Okay? So what this says is that the faster an airplane goes, the more power the engine is going to need to use, okay? And actually it increases dramatically. It increases as the cube of the speed, okay? So if you go twice as fast, that double gets cubed and you get 8 times the power output of the engine. So the power output rises dramatically with speed. So what do airplanes do? Because the power output of the engine is obviously limited by what kind of engine you're using. So how do we handle this? Well, what an airplane will do if it wants to go fast is it will go up high into the atmosphere, okay? And when you go high into the atmosphere, the drag coefficient drops because the atmosphere is thinner, and so you can go at the speed you want to go at while staying within the constraints of your particular engine, okay? So yeah. Type it in the chat if you know the fastest jet that has ever been made. I want to know who knows about aviation. What's the fastest jet ever made? Okay. Let's do another example. Let's suppose that you're going to lift something. So you're going to lift a weight. All right? You lift a mass, M, a distance, D, with a force, F. What is your average power output? To my knowledge, the fastest airplane is the SR-71 Blackbird, which went around Mach 3. I've actually seen one fly before because I was obsessed with the SR-71 Blackbird when I was a kid. I had a giant poster of it in my bedroom. The reason that this airplane could go so fast is because it went almost into space. Like the pilots were wearing spacesuits. And it was a spy plane, so it had really good cameras on it. And if an enemy detected the SR-71 Blackbird and fired a missile at it, the SR-71 Blackbird would just accelerate and go faster than the missile. So it was a really cool plane. And one of my favorite kill streaks in Call of Duty. If you ever played Call of Duty Black Ops, it had the Blackbird kill streak, where you could know exactly where everyone is. That's a really good question. How do you capture good pictures, video while going so fast? I don't know. That's a really good question. I would imagine you'd have to have some camera that is able to, rotate at the exact rate that the image. Now, keep in mind that you're so high up that you're going really fast. Even though you're going really fast, you're so high up that your vantage point on the Earth is not changing terribly rapidly. But I would also guess that it probably has a camera that might have a very fast exposure, so it doesn't need to, the shutter doesn't need to be open for a long time. Or it could have a camera that slowly moves depending on the speed and altitude of the airplane, so that it always stays focused on the same location on the ground? I'm not sure. That's a really good question. Okay, so we lift a mass, m, a distance d, with a force F. What is the average power output? Okay. Now, why do I say average power output? Because if you're lifting it with a force F, it's going to accelerate upward. So its velocity is not going to be constant. Okay. So if we work this out, so we've got an upward force F. Okay. We've got a downward force mg. So doing Newton's second law, the net force equals ma, which means that F minus mg equals ma, which means that the acceleration is F over m minus g. All right. So now we use, okay, so now we use we use the kinematics equations. For example, delta x equals 1/2 at squared. The delta x is a distance d. And then the acceleration is F over m minus g times t squared. So we can see that the time it takes to travel the distance d is going to be 2d over F over m minus g square root. Okay, that's the amount of time. So then the average velocity is going to be distance over time, which is going to be d over square root of 2d over F over m minus g, like that. Okay. And let me simplify that. So we have let's see, d over 2 times F over m minus g square root. So that is the average velocity. Okay. That's the average velocity. And so if we want to get the average power, I think I did this right. I would do force times the average velocity, which would basically take this and multiply it by force. So I would get, now when I multiply f into the square root, I'm going to square it. So I get d over 2, square root of d over 2 times f squared times f over m minus g. All right. So yeah, this is kind of a cool equation. So notice that your average power depends on the force that you apply. All right. I like that. And this is a common thing. So oftentimes the power is a function of some variable. Okay. And you want to find the maximum power, right? Because you want to, like if you're talking about engines, you want the engine to output the maximum power possible, okay? So you take the derivative of the power with respect to that variable. And so I'm putting x to be just an arbitrary variable. This doesn't mean position. It could mean anything, okay? You take the derivative of the power with respect to that variable, and you set it equal to 0. Okay. And then you can find the maximum power point, which is really cool. Okay. This is basically what's going on if you are riding a bicycle or in a car and you're changing the gears. What you're doing is you're changing the gears in the bicycle. You're applying a torque on the pedals. Okay. And depending on the gears, that torque is going to get you a different rotation rate. Okay. So different gears are giving you different pedaling rates and you're applying different torques. And there's a certain gear setting where you have the maximum power. And so that's the gear that you would want to set your bike at in order to ride as efficiently as possible. Same thing with cars. If you put the car in the right gear to maximize torque output of the engine times rotation rate. It's pretty cool. All right, so I will see you in the Zoom room. That's all.